So I was saying that as we study life, all the life that we find out there is based on carbon. All life on Earth. Now, life on Earth can have, can use things other than carbon. For example, certain diatoms can build silicon shells, but the actual genetic code of the diatoms is still carbon based, and they're all based on the same basic building blocks. And so that becomes very, very essential. Even things like viruses, which don't have DNA, they're still based on these same sort of building blocks. And that's basically how life works. And DNA replicates. Again, this is how viruses get you, is viruses can come in here and take over this process and then reproduce themselves. Okay, so they can start reproducing themselves in here instead of your own genetic code. And if they don't reproduce, they can actually encode their genetic code in you. So you get a virus and you get better. Well, you don't always get better, because sometimes the virus actually changes your DNA. In fact, a large portion of human DNA is viral DNA. Well, a couple of scientists, Miller and Urey, did an experiment a number of decades ago, seeing, can you make amino acids? So what they did was they replicated the original atmosphere of Earth, which was, had some nitrogen in it, some water vapor, carbon dioxide, some hydrogen maybe. Oxygen wasn't there. You needed life to make oxygen. And so they shocked it, with some electricity, basically simulate what lightning would do. And after they ran this for a while, it started making a mixture of amino acids. And so they call that a primordial soup. Now, the idea is these amino acids could possibly come together and then form life. Now, how that happens, I don't know. That's beyond the level of this course. None biologists really understand how that works. We've never made life in the laboratory. We've modified life in the laboratory, but we've never created life out of nothing. And so that's this idea of a primordial soup just simply says these amino acids could be produced naturally. And we know that the primordial soup did possibly exist. We know that these amino acids are produced in the protelids and in the comets. And so, and it could be that they were delivered to Earth that way instead of being originated on Earth. But biologists still don't really understand how life came about. So this is a big question. Some say, well, if you get the right ingredients, you wait long enough, then eventually they'll start replicating and making life. And others say, no, it's very difficult to make it do that. And so in that case, that life originating would be very, very rare. Okay, so that's one of the issues. We don't really know. We are pretty sure, though, we need water. Water is made of hydrogen and oxygen. Okay, hydrogen, one of the most common things in the universe. In stars, hydrogen fuses to helium. Helium fuses to carbon. If a carbon grabs an extra helium, it becomes an oxygen. And so oxygen is fairly common as well. And so that's good. The other thing is water is liquid at just the right temperature. If it's too hot, carbon chemistry doesn't work real well. That's why, a high temperature can kill you. It messes up your amino acids. Okay. And in fact, that's how your body tries to kill an infection, is it raises the temperature to start messing up things up and interfering with viruses or things replicating, because they don't do as well at high temperature. You don't either. And so the question is, does it kill the infection or kill you first? So that's what temperature does. If it's too cold, then the reactions don't work so well. So if you get too cold, then you quit having the chemical reactions. That's hypothermia, and then you die. And so you got to be at the right temperature. Water turns out to be liquid at just the right temperature for organic molecules or carbon-based molecules. Water's also polar, meaning that it's got plus and minus sides to it, so it's a very good solvent. It's able to move other molecules around very easily. So other things don't do that. So that makes water a perfect thing. So that's why when we look at another star, we define something called the habitable zone, or sometimes called the Goldilocks zone, as the distance at which water can be liquid. If you're too close to the star, it's too hot. If you're too far away, it's too cold. If you're at just the right distance, water could be liquid on a planet. And so that would be the right place to look for life. Now, this is what we call the traditional habitable zone. It is possible that you could be outside the habitable zone and weird conditions could happen. For example, you could be too close to a star, but you might have clouds that block some of the sunlight and keep the planet just barely cool enough, or it might be cooler underground. You might be outside the habitable zone, but there might be like a massive greenhouse effect that keeps you going, that keeps you warm. Or one of the moons of Jupiter, tidal interaction with the Jupiter, even though it's way outside the habitable zone, tidal interaction with the Jupiter stretch it and squeeze it and heat it up so that it actually has liquid water on it. So it is possible here to be outside the habitable zone and still have liquid water, but this is just the basic idea. And so if you look at the solar system, now actually how you define the habitable or habitability zone is a little bit different, because some people define it a little narrower, some people define it a little bit wider. Obviously, Earth is in the habitable zone. They argue whether Earth is in the middle of the habitable zone or near the outside of the habitable zone or near the inside of the habitable zone. And so they actually, modern feeling is Earth is probably near the inner edge of the habitable zone, and then Mars is just outside, and Venus as well. So that's the idea. But for the different size stars, for cooler stars, remember lower mass stars are going to be cooler stars like red dwarfs. You have to be very close to being in the habitable zone. For stars that are hotter, you can be farther away and still be in the habitable zone. And so the size of the star matters. One of the problems you run into, though, is if the star is too small, like a K or an M star, the habitable zone is so close to the star that tidal interactions of the star keep one side of the planet always facing the star, what we call synchronous rotation. There's huge debate over whether the planet in synchronous rotation really should even count as being habitable. It might be in a habitable zone, that is the right distance and liquid water, but if one side is always facing the star, it's too hot. If the other side's always facing away, it's too cold on that side. And so, on Earth, the Arctic and Antarctic are facing away from the sun for several months of the year, and look how cold they are. Okay, what would happen if they were facing away from the sun forever? Okay, then you're not going to have life. Okay, and so, and the in-between zone between the two, it's going to be so stormy, it might not be suitable for life. And so they have a huge argument over whether a synchronous rotation planet really is even habitable. They're not sure. And again, even with a star that has a habitable zone, over time the habitable zone changes. Even for the sun, when the sun was much younger, it was a different brightness, and it's possible the habitable zone was wider. At the current age, the habitable zone includes Earth, but in the future, the habitable zone might actually, in 1 billion years, be outside of Earth's orbit, so Earth would not be habitable anymore. We already talked about that as to how stars die, that in the distant future, Earth will not be habitable. So that's another thing to consider. But you could be a habitable planet outside the habitable zone. I talked about the moon Europa, one of the moons of Jupiter. It's caught in a tidal tug-of-war between Jupiter's other big moons and Jupiter itself, and so it stretches and squeezes it, and that warms the interior, and so the surface is coated in ice because it's too far from the sun to be warm, but underneath the ice we have reason to believe there's a large ocean of salt water. So that's, and it may even have the right ingredients for life. Enceladus, this is a moon of Saturn. way too far to be the habitable zone, but there's indications it's got geysers of water spewing up from it, and so there is potentially a large ocean or reservoir of liquid water under the surface, heated partly by tidal interactions and partly by radioactive decay, and also kept cool by sort of a natural antifreeze, ammonia salts. So again, there are other possibilities out here. Maybe life not as we know it, but life that we could recognize as life. Speaking of life not as we know it, there are some life forms even on Earth that are darn weird. As I said, you get too hot, life doesn't work very well. But there have been life forms that have been discovered in living bacteria living in hot springs in volcanic parks. Places like Yellowstone National Park, where you have the geysers and the hot springs. It's way too hot for life, they thought, but they did find a few bacteria that live in these superheated environments. It turns out that there's a bacteria that's been discovered growing on fuel rods in nuclear reactors. So radiation that's thought that it would kill anything except this particular kind of bacteria. And so there are a few extremephiles. So these are organisms that will live in these extreme environments. So even though you might have a planet that has extreme environments, it is remotely possible that life could live there. And so, but it's a question whether life could evolve or originate on an extreme environment, or would life simply adapt to the extreme environment.